All right, good morning grade 9s. Welcome to your little lecture on topic 6, where we're going to discuss generators and motors. Now guys, we're still kind of continuing this theme of one form of energy turned into another form of energy, and of course in this unit it's all about electricity. So in our last topic, topic 5, we were looking at how chemical energy is converted into electricity in the case of cells and batteries. And today we're going to talk about mechanical energy providing us with electric energy, and mechanical energy usually involves something moving. So first we're going to start talking about generators. So generators are the main way that we generate electrical energy. And in Alberta, we often use steam that's generated from burning fossil fuels, and that steam power will create movement, which in an electric generating facility will cause electricity to be produced. All generators have to convert some kind of motion into electricity. So it could be the case of wind power, moving these blades, which causes a rotational motion to make electricity, or maybe we could even use water power in the case of water being used to move a wheel or a turbine to create electricity. Now guys, the only way that this actually works is because of a very special relationship between electricity and magnetism. A scientist by the name of Hans Ørsted discovered that if you had a current moving in a wire, it would deflect a compass needle when the needle was brought close to the wire, inferring that the moving electrons, the electricity, was creating a magnetic field that the pole of that compass was responding to. Now, if you take that coil of wire and you wrap it around a metal and you turn the power on, that has the ability to actually magnetize that piece of metal. So if I go to the next slide, cooperates with me, you can see a diagram of that right here. So there we have an iron nail. We've got it connected to a circuit, and loops of the wire are wrapped around the nail. So when the power is turned on, there is a magnetic field generated by the electrons moving in the wire, which cause the whole nail to become a magnet. And it's called an electromagnet because we're providing electricity to produce some magnetism. Now you guys need to know what 3 factors could increase the strength of this electromagnet. So those are, of course, right here. Simply use a more powerful source. So hook up a few more cells for that power supply. Provide a greater amount of current and you will get a better magnet. Or make more loops of wire around the nail. That will also make it a better magnet. And lastly, not all materials get magnetized the same way. So depending on what that core is, what kind of metal it might be, would also cause it to behave as a better electromagnet or not. You can see in this diagram here, guys, a practical application of an electromagnet is when in a wrecking yard they want to move cars around or move cars to get them crushed. They have a very powerful electromagnet that they create so that when the magnet is on, when the current is on, the magnet works to pick up even the weight of a car, and then when you want to drop the car, simply turn the current off. It's not a magnet anymore, and that car will simply fall. Now, so guys, we're still talking about how can we then use magnetism to generate electricity. Well, Michael Faraday, another scientist, discovered that a moving wire, so the wire didn't even have to be connected, a moving wire in a magnetic field will generate electricity. See, so that's sort of the opposite relationship that Hans Ørsted discovered. And this is really the basis for how a generator works. We're going to use magnetism to generate electricity. All you need is to have a moving wire in a magnetic field. Now, when it comes to generators, there's mainly two kinds. There's AC generators and there's DC generators. And no doubt you've heard the terms AC and DC being thrown around. It's not just a music group, but it's different kinds of electricity. And so the AC stands for alternating current, which means that the electricity goes back and forth in the circuit. Whereas DC, which stands for direct current, means that the electricity or the electrons are flowing in one direction only. And so sometimes you want to create a circuit and it's perfectly fine to have the electrons moving back and forth. And then at other times you just want it moving in a singular direction. So we're going to talk first about how we make an AC generator. The basic parts of generators are the same. Guys, we need a stationary magnetic field created by a north pole magnet and a south pole magnet. And then we need a rotating loop of wire, which by the way would be called the armature. So the part that's moving in the circle is the armature. And then the loop of wire needs to make a circuit. So then it's connected. One wire is connected to this slip ring, and another wire is connected to the other slip ring. And then of course we have these brushes which maintain contact with the metal slip rings. And then of course we need our circuit, which is going to be connected to a resistor or a load so that it can do some work for us. All right, now the best way for you to actually see what's happening here to create the flow of electrons is a little video that I'm going to show you, guys, which again, remember, it works on the principle that these wires, when they're moved in the presence of that magnetic field, causes the electrons to actually flow in the wire to generate that electricity. So I'm just going to start the video up, and I'd like you to watch that, and then I'll come back and then we'll have to talk about motors.
In the magnetic field to continuously induce electric voltage and current. But current produced in this fashion has an interesting feature. It is alternating. We can better understand this characteristic if we study the coil's rotation. Note that the particles flowing through the circuit represent electrons, but keep in mind conventional current flow is opposite in direction. By looking at this simple generator, we can see most current is produced when the conductor passes through magnetic lines of flux at the fastest rate. That is, the greatest current occurs when the conductor moves at right angles to the magnetic field. Then, as the conductor continues its rotation at a constant speed, it cuts through fewer and fewer lines of flux, and less current is induced. Eventually, the conductor moves parallel to the field. At this point, no current flows because the conductor doesn't cut through any lines of flux. This occurs twice in each revolution. Notice, as the coil rotates, one of its sides cuts downward through the magnetic field, causing current to be induced in one direction, while the other side is moving upward, inducing current in the opposite direction. After the coil passes through the position of no current flow, the previous downward side moves up, and the previous upward side moves down, thus reversing the current flow in the external circuit. This, then, is alternating current, a flow of current in a circuit that reverses direction periodically and is continually varying in magnitude.
All right. So guys, I just wanted to stop there for a second to let you know that now we're going to subtly change the generator so that it will keep the electrons flowing in the same direction. And that's done with the help of what's called a commutator. And so I'm going to let the video continue, and so listen for exactly how this commutator is going to change and keep the flow of electricity in the same direction.
So how can we construct a source of direct current? Obviously, we must find a way to maintain current flow in one direction in the external circuit. To do this, we need change only the slip rings, which collect alternating current, to a commutator which will rectify, that is, change AC to DC. The commutator is a collar divided into segments, insulated one from the other. We attach one end of the coil to one of the segments and the other end to another segment. Now, as the coil rotates through the first half cycle, the induced current of one direction is collected from the commutator segment. It flows through the external circuit, then back to another commutator segment and into the coil, completing the circuit. The brush that connects the commutator to the external circuit breaks the contact with the first commutator segment and makes contact with the second. As we've seen, the induced current in the rotating coil is opposite in direction from that of the previous half cycle. But the commutator switches the coil connections to the opposite side of the external circuit. In the external circuit, the current generated from the second half cycle is in the same direction as that generated from the first half cycle. The commutator has rectified the current, converting it from an alternating current to one that flows only in one direction, direct current. But there is a problem. The direct current produced by a single coil is pulsating and unsuitable for most applications. Therefore, practical generators have many coils and many commutator segments that can produce a voltage that pulsates very little and is usable.
All right, so I'm back. So I hope that helps to explain how you get the electric current in the first place, as well as can we take that alternating current and just by using a split ring commutator, keep the electrons moving in the same direction. Now, guys, before we go to the next slide, if you take a look at the bottom of this slide, it talks about the fact in North America, the direction changes. So if you have an alternating current generator, the direction changes 120 times per second. So that loop between the magnet is actually rotating very, very quickly. Now that means that it completes a whole cycle of going all the way down and then all the way back to where it started, 60 times per second. So we call that its frequency, and the unit that we measure frequency in is hertz. So we would say that this particular generator is generating AC current at a frequency of 60 hertz, which machines that are designed for that electric current or to work on that electric current will work. But if you're in another part of the world, England for example, they would use a different generating system that generates at a different frequency, and that's why when you go to foreign places sometimes you need adapters to make your devices that are created in North America to even work. Well guys, now if we go to the next slide, that's just a close-up of what we were talking about. This is the slide that just talks about how DC generators create the current in one direction using the commutator. So you were able to see that on the video. So again, hopefully again, that made sense. These videos, by the way, guys, are in the Google Classroom in the video review section, so that you don't have to go back to this YouTube clip. You could simply go there. All right, so now we're going to turn our attentions to a motor. Now this time, the motor is going to take electrical energy and produce mechanical energy or motion. So so this is what happens if you have an electric lawnmower and you plug it in and you flip the switch, you turn the power on, and then it's going to make the mower blades spin, or a blender, for example. Those are examples of electric motors, and again, they work on the principle that magnetism and electricity are related. Okay? this time, and many of the parts of a motor, guys, are the very same parts of a generator. It's almost as if we're working in reverse. So we are still going to have a loop of wire. We're still going to have, which is going to be able to be rotated when essentially electricity flows in the loop, which is going to create a magnetic field that works oppositely to the magnetic field created by this part of the motor, okay? And that will cause it to spin, sort of, because we know that magnets repel each other. So we're essentially creating an electromagnet in this part called the armature, which is going to spin because it's generating its own magnetic field, which is opposite to the magnetic field. And one side of this magnet will attract the armature, and one side of the magnet's going to repel it. And that's going to keep it moving in a spinning direction. All right? Again, these motors can be AC motors, which has the electrons flipping back and forth in terms of their direction, which actually works quite nicely, as you'll see on the video, for allowing the armature to continue to spin in the same direction. Or we could actually use a DC motor, which is going to provide direct current. And in that case, again, since we want to actually flip the direction of current in the armature so that it keeps moving, is going to need to use a split ring commutator. So again, the video will help you understand that, because it will show you everything in motion. Okay? You're going to hear some of this terminology. Remember, you should be familiar with this vocabulary when it comes to motors and or generators. So remember that the armature is what spins inside the magnetic field. Of course, we have our conducting wires. You have to have some kind of source of electricity, whether it's AC or DC for your motor. You're going to have a magnet that stays in place. That's sometimes called the word escapes me. The stator, rotor is the part that moves, that's your armature, and it's like stator or something like that. Then we have our brushes, which need to make contact with the spinning slip rings or the commutator, and there we go. Okay. All right.
Possible. It looks like this. And the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system.
Right, and we can stop that video there, guys. So again, very quickly, we've got a DC power source. You saw that it was a battery. It's providing the electron flow, and the electron flow moves through the brushes, which is attached to the split ring commutator. Remember, the split ring commutator is going to allow the direction of electricity, or sorry, yes, the direction of the electricity to alternate, because we actually want to make it go back and forth so that this armature will keep spinning. And of course, this spinning armature could be connected to blades in the case of a mower or a blender or anything else we want to cause to spin when we turn on the electricity. So I hope that makes sense. We'll see you next time.